So lab 5 will be about, again, about simulation and computation. We'll be looking at 2 cases of simulation, and then we're looking at 2 different types of computation regarding the normal distribution. So if you could just turn to page 52, and we'll take it from there. So please just turn to page 52 of your lab manual. All right. The first thing I want you to know is how to simulate an unknown discrete distribution. So I will set up an arbitrary distribution. This is just an unknown discrete distribution. So you have possible values of z and probability that z equals this. So z could be 1, 2, or 3.
This is question 1A.
No, this is not directly related to that question. This is just an example to help you try to solve that question. Okay, this is just an example to try to do, because I don't want to directly approach that question. Question 1. It's a big lab. I can't go through everything. So I'll focus more on 2 and 3, especially 3. But I want to just give you the means of simulating a random discrete distribution. Now, if you did lab 4, you probably already did something like that in the first question. So this should be a review in a sense. But let's look at this discrete random variable. It has 3 possible values. The probability that you have z equals 1 is 0.7. Probability you have z equals 2 is 0.3, and then 0.2. So add up to 1. So probability that z equals 2 is 0.2, and probability that z equals 3 is 0.1. So this is just an unknown discrete random variable. And we want to be able to use Minitab to simulate this variable. If we have a known discrete distribution, like we did last time, we had known binomial distribution, or we have a known Poisson distribution, then we follow a procedure that I tried to explain last time. In this case, this is an unknown discrete distribution. How do we simulate this? Well, first you prep the columns on Minitab. So in C1, you will input the possible values of this random variable. So you do 1, 2, 3. Because this random variable has 3 possible values. And then in column C2, you will add the probabilities of each value. So in this case, 0.7, 0.2 for 2, and 0.1 for probability that z equals 3. Then, at this stage, you do the same thing you did last time. You go to cal random data. Okay? Go to cal random data, and you choose this option, the discrete option. This is an unknown discrete distribution. So whenever you simulate, you use calc random data, and then you click discrete. Now, let's say you want to simulate 1,000 values of this distribution, from this distribution. So you do 1,000 for number of rows to generate. You store the results in C3, because that's where you want to store the results of the simulation. And the values in are the possible values of the random variable, which are in C1. The probabilities are in C2. And that's the process. And then you click OK. So just have a look at that. This is the case where we want to generate 1,000 copies of Z. Okay? And you get that number pop up. Any questions about this? Do you now know how to simulate an unknown discrete distribution, right? What should be apparent to you is how closely it mirrors the other simulation processes we discussed last time. Okay, that's the first point I wanted to make regarding question 1. For question 2, I'll start looking at specifics, starting with question 2a. So question 2 is about simulating, in general, big picture, it's about simulating a normal random variable, and we pick particular members of this normal distribution. So the normal distribution is a family of distributions, and each member of the family is specified by two parameters, the mean and the standard deviation, right? That's what I meant when I discussed last time that question, when I asked you how many parameters determine the normal distribution. What I meant to say, I guess, to be precise, absolutely precise, is how many parameters determine a precise member of the family of normal distribution? Because normal distribution is a family of distributions, right? Okay, so let's simulate a normal distribution. Question 2a asks us to do precisely that. It says, simulate 100 random values from a normal distribution specified with mean 60 and standard deviation 8. Okay, so one thing you can do is you can, because it tells you to save in C1, you could just close this and just open it again if you want. Or, there's other ways of doing it, but because I just want a new sheet for this question. So you go to Calc, Random Data, and you go to Normal. So everything should be clear on your worksheet when you start this question. This is for A. This is question 2A we're looking at right now. All right, everyone's following that? And then you click the number of rows to generate. So how many rows do we generate in this case? 100, because they ask you for 100 copies of the simulation. So everything should be pretty straightforward. They tell you save the results in C1. So the results should be stored in column C1, the results of the output, the results of the simulation. Now we specify the normal distribution by the two parameters. The mean is 60 in this case, and the standard deviation is 8. Right? So that's what your input should look like. It's pretty straightforward. Mirrors the binomial case very, very heavily to a large extent. Then you click OK, and you get 100 values of the normal distribution, this particular normal distribution. All right, I want to also just repeat this process for D and E, just to give you an idea. So it says, repeat part A to C using a sample of 500 random values. So the same, you stick with the same distribution in part C. Now we're referring to question, okay, before I move on from question to question 2C, I should probably stop and ask you any questions regarding this.
Yeah, because I used the numbers of the normal distribution.
Sure. Cal, random data, normal, and these were the numbers that I used last time. That's 100 at the top. And C1, 60 and 8. All right? Did you get the numbers this time?
We got different numbers,
Yeah. Oh yeah, you're going to get different numbers because it's a simulation, right? You're going to get different results for simulation. For computation, you'll get the same results. So for simulation, you'll get different values over here. Everybody will get different values. Okay. Let's go back and simulate. Now we're going to question 2D, and it says use a sample of 500 values. So you go to Calc, Random Data, Normal, and now you just change the number of values to 500. They're not asking you to change the distribution. It's the same normal distribution, exactly the same one. So the parameters stay the same, 60 and 8. But the number of simulations change. And you store the result, obviously, in a different column. In this case, you store it in C2. So the length of C2 should be 500. Okay? All right, any questions regarding that? We just changed the number of simulations. That's pretty obvious, right? It's pretty clear because you've done so many simulations by now. Lab 5, just to mention it, is a bit of a long lab. It takes a while to do. It's not complicated, but it takes a while to just do everything. But lab 6 will be conversely quite easy. So we'll get through that fast. So this is going to be a bit long, possibly the longest lab in the, well, maybe not the longest, maybe the second longest in the whole.
Professor, how many numbers, like, so where do you want to stop it?
Just the first 30, it's fine. I'm not picky about that. I'm not picky about that. Okay, I think that's enough for the question 2. The only thing I want to point out about question 2 that's a bit irregular is that in question 2I, it says something a bit strange. It says, construct the box plots for data in C3 to C5. That's okay. Then it says, use the multiple Y option. Don't worry about that. Just cancel that part. Don't use the multiple Y option. Just construct the box plots for data in C3 to C5. That's all. Just copy and paste those box plots. I don't want to know about the multiple Y option. Okay, so what we've done so far is we've explained, we've sort of talked about how to simulate. Yeah, you have a question?
For D and E, we also use the normal distribution.
The same one, yeah.
Same one.
Yeah. So what we've done so far is we've talked about how to simulate an unknown discrete distribution, and we've seen how to simulate a normal distribution, a particular normal distribution. Now, what we want to do is we want to mirror what we did last time. We want to do a computation given a particular normal distribution. So we'll be given a particular normal distribution. In other words, we'll be specified the mean and standard deviation. And then, on that basis, we'll go ahead and do a computation. So we'll see how to use Minitab to do that. Again, this mirrors what we did last time. That's question 3. Question 3 talks about the height of women in the US, and it claims that this is normally distributed with mean 64 and standard deviation 2.75 inches. In that statement, the normal distribution is specified. So the mean is 64, and the standard deviation is, what was it, 2.75? Yeah. Inches. So how do we use that information to compute? Let's look at question 3a. It says, find the probability that the height of a randomly selected woman is less than 61 inches. So here, we go to calc, random data, no, probability distribution, sorry, and normal. Since this is a computation question, we will choose the calc probability distribution option, as opposed to the calc random data option, which we did for the simulation case. So we go to calc, probability distribution normal. And here we'll use the cumulative probability in the first feature, because this is a normal distribution, it's not a discrete distribution. And you'll first specify the distribution. The mean is 64. The standard deviation is 2.75. So that's all straightforward. But here we will move to the input constant, because we'll pick off particular values from the normal distribution. We won't have an input column like we had for the binomial case. In this case, you'll pick out particular values. So we'll be inputting those values in the form of a constant. So we'll specify the input constant. In this case, the question asks for the probability that x is less than 61. So the input constant in this case will be 61. Okay? And what that will give us when we do all this is this probability. Probability that x is less than or equal to 61. So all this process will give us that probability for that distribution. Okay? So again, you go to the cumulative probability option, you specify the distribution, you go to input constant, and you specify that as 61, and you click OK. And then Minitab itself will output the probability, which is 0.137. So the probability that the height is less than 61 inches is about 14% or 13.7% to be precise. Okay, any question? Yes.
I don't understand how what we type in the box means that x is less than. That would mean that if x is equal, in that case, because it says constant.
Well, you know, we have a continuous distribution. So in a continuous distribution, the probability of any particular number is technically 0, right? It's only when you talk about intervals that you can assign probability in a continuous distribution. I'm sure you've learned that, right? In a discrete distribution, it makes sense to pick out certain points and specify their probability. So for example, I specified a discrete distribution with only 3 possible values. So the probability of the first point was 0.7. In a normal distribution, since it's continuous, any one particular point has actually a 0 probability. The only thing that has probability is an interval, right? So in this case, the probability that x is less than 61 has a value, has a well-defined value. That's very important to understand. And it goes back to the difference between discrete and continuous distributions. I mean, that's right. That's very important to know that. It's very important to understand that for a continuous distribution, picking out particular points is not meaningful. You need intervals to specify the probability, right? So for example, if you draw this, let me just illustrate that by drawing this. If you have this normal distribution, so this was 64 mean. Right, it's not a good picture, but if you want the probability of x equals 61, this thing, it'll be 0. But if you want the probability that x is less than 61, it'll be this area, right? So then that makes sense. The area under the curve is exactly the probability, right?
And why is it not a problem for the discrete one? Is it because it's not
Because a discrete distribution will look like this.
large?
Yeah, exactly. It will be like 1, 2, 3, and this has probability like that. This has like this, and this is like this. So it's well defined in particular cases. It won't be continuous. There's nothing in the middle over there, right? It's important to understand that. It's a good question. It's a really good question. So, any question regarding 2A? I think that specifies that, right? Okay, B I want to leave for you. C, I'll do for you. Okay? Find the probability that the x value is greater than 70. So now, the question asks you a probability that x is greater than 70. What is the probability that x is greater than 70? What we know is how to compute the probability that x is less than or equal to 70, right? Once we get that, we can just take the complement of the area, which is 1 minus that, to get the probability that x is greater than 70, right? So first, let's go and compute what we know how to do, which is find the probability that x is less than or equal to 70, okay? And we do the same exact procedure. Go to Calc, probability distribution, normal. You keep the same settings for the cumulative probability. You keep the same distribution, and you just change the input constant to 70. And now you'll get this value. So graphically, if this is 70, you'll get this whole area. All the area this side, to the left of that value. You got that values? And you get 0.985. So the probability that x is less than or equal to 70 is 0.98. 985. That's good enough. So this area is 0.985. Since the whole area is 1, this greater than area will be 1 minus that. 1 minus 0.985 will be the probability that X is greater than. So that will be 0.015. 1.5%. Any questions on that? That should be pretty clear. Yeah.
For part B, because it's between 61 and 70, how can we
Yeah.
put the numbers inside the...
This one I want you to think about, right? I don't want to do this one for you, right? This,
No,
this.
I know, but I
Right.
don't know where to put the numbers. I want to ask this question.
See, you only putting numbers. You'll be doing. You can only find the probability that X is less than a certain number. Okay.
Yeah, okay, but for this question, it's between. That
Yeah.
means we write 61 here and then 70 on there, and another box on there.
No, you do it step. You first look at 61 separately, and you look at 70 separately,
Oh, okay.
and then you go ahead. I mean, that's the hint I can give. I don't want to do that for you, right? That's the one part of the lab that I want you to think about. The rest is pretty straightforward. There's nothing there to look at. All right, so D I'll leave to you as well. E I'll do for you, and for F I'll give you a hint. So E, now we're going to use something a bit different. It says, what height represents the 97th percentile? Okay? Yeah.
For that B, I didn't get the same answer.
Yeah. For what?
For this B,
No, this is, sorry, this is
this is
C. This is C. This is sort of a mistake. This is C. This is C. All right, now we're moving on to question 2E. Okay? What height represents the 97th percentile? Okay, so now there's a function in Minitab that given a particular percentile, you can pull back the value of X that corresponds to that percentile, right? So for example, in this distribution, what is the 50th percentile? What value of X corresponds to the 50th percentile, or the median?
64.
64, because the median is the mean in this case. So 64. If you have something over here, that would be like the 10th or the 5th percentile, right? If you had something over here, that would be the 99th percentile. You have to have a bit of understanding of the percentile idea. It's basic, but I assume you already know that, right? You've taken percentiles. Like for example, the first quartile is the 25th percentile, right?
Yeah.
Okay. So the second quartile is the 50th percentile. Third quartile is the 75th percentile. Okay. So the height that represents the 97th percentile. So again, we use the same calc, probability distribution, normal. In this case, you look at the inverse cumulative probability because you're going back. You take a percentile or a probability and you go back to the value of X. In the first case, you took a value of X, you took a value of X and you went to the probability. Now you're doing exactly the opposite. You're taking a probability or a percentile and going back to X. Right? So that's the inverse feature. And now the input constant, you have to be very careful here. It's 97th percentile, so what do you write?
The probability.
Yeah, the probability, what is it?
0.97.
0.97. Don't write 97, because you won't write the probability. That was the point. And in this case, the value of X that satisfies that is 69. So which height represents the 97th percentile? It's 69 inches. Okay? Any questions regarding this 2E? Okay, good. So for 2F, I can give you a hint. You just have to do it for the 25th percentile, because the first quartile is the 25th percentile. I'll leave that for you, but all they want to know is for the 25th percentile, so it's the same process, the inverse cumulative distribution for that. Okay, and that is the lab. This lab is a bit long to do, but I think those ideas will be more than enough for you to work on that. Lab 6 will be very easy, so we'll get through that very quickly, and it won't be much work for you as well. So this is, you can think of this as a unusual lab in some ways. I'll put the homeworks out over here, and I'll take the labs that you put away. Okay. Thank you.